The name of this video is Surface Polarization Charge. So finally, we'll use what we developed in the past two videos to find, so before, first of all, we analyzed qualitatively the behavior of the surface charge distribution, sigma p. We then analyzed the behavior of rho p, and now we will use the equation, the general equation, to find the charge entering an inner region of a dielectric material to find sigma p, not only qualitatively, but actually quantitatively, okay? So it's surface polarization charge. Great. So in order to find the surface polarization charge, the best approach, in my opinion, is to start from something a little bit more general and then look at the surface of one single homogeneous dielectric material at the end as a sort of final result, as a sub-case of what I'm about to do. So in order to set up a more complicated problem, more advanced and more general problem, let us consider a dielectric material, and a solid made of two different dielectric materials. So let's sketch them. Let's say the one is green and one is blue. Okay. So one part of the dielectric material resides in this region of space. It could be something like this. And it has a boundary here. Let's make it a sharp boundary for simplicity, because it doesn't have to be like this in real life. The other one has a boundary coinciding with this one, so it's adjacent to this other material here, and it continues in this fashion here. All right. So the material on the top side here, we say that we assume that it's part of a region of space capital omega 1, whereas in the region below, this region is capital omega 2. Good. As it turns out, let us assume that capital omega 1 is characterized by a polarization charge in the volume with density rho p1. Somebody gives it to us, pre-calculated it for us, and it gives it to us. Whereas rho 2 is characterized by a rho p2, obviously. Okay, so these are two adjacent materials. Now, I want to investigate what happens at this interface between two materials, which effectively constitutes a discontinuity, because I have a uniform homogeneous material here and another homogeneous material there, and then there is a discontinuity between these two materials at this interface right there. And so what we do, we consider a point, let's consider a point capital Q right here, as always. And I want to investigate the properties of P, the polarization vector, capital P, as well as all the polarization charges in this region of space. Okay, so how do we do that whenever we have a discontinuity? So the first question I have for you is, I have a discontinuity, so this interface between two different homogeneous, each of them homogeneous dielectric materials, the interface represents a discontinuity. So, if you go back to Phys 242, when did we study discontinuities? When? In a number of different situations. One of them was when we investigated the local form of Maxwell's equations for the electrostatic field as well as for the magnetostatic field. So the local form of the Maxwell's equations, in the presence of a surface charge distribution, can we use the divergence, the curl, etc. in that case? Think about it and come back. The answer is no. What you need to do instead is to use case 2 of what we've done in Phys 242, which is the local form of Maxwell's equations, which is not the differential form that was case 1. So we need to use something which is like case 2 in 242, local form, but not differential form, because we cannot use gradients, we can use curls, we can use divergences in this case, because it's a discontinuity. At least we should not do that. We can always use the integral form, and which is what we are about to do here. And so whenever we have a discontinuity of this type, what do? We consider in the neighborhood of a point capital Q, for example, in this case, is something like Gauss's theorem. Remember what we have seen in the previous video, is the flux of P what gives me the charge, so it's like Gauss's theorem. So I use a coin type surface, which is a cylinder, in the neighborhood of this point capital Q. All right, so let's sketch our cylinder here. So the cylinder will be characterized by a surface here above and a surface below. So there will be the lateral surface of the cylinder, and eventually there is a surface below right there. All right, this is my coin. This is my coin type cylinder. Okay, why is a coin? Because eventually we make it so small that it really becomes a little coin about capital Q. And of course, in this region about capital Q, we can also identify an area here. This area is dA. We go straight to the differential case. So instead of delta A, let's go straight to dA. This area is dA and is around a point capital Q, okay, which is right there. And so as always, now we need to choose our normal unit vectors. So we choose N1 in region 1 to point in this direction. We choose N2 in region 2 to point towards omega, capital omega 2. So it's this. By definition, we choose N to point as N1. So N is actually an N, if you really want to be precise, underscore to 1. Okay, this is this N, which is what we call simply N. But we should not forget that it's to 1 from region 2 to region 1. We always go from region 2 to region 1 for anything that has to do with the electric field. And when it comes to magnetic field, it's better to do the other way around for some reasons which we have seen in 242. Okay, if you remember that for the local form. All right, so we have this coin is characterized by two bases with area dA, one around capital N2 and one around small n2 and one n1. The lateral surface is whatever it is, completely arbitrary. All right. So now that we know that, we also want to specify the surface density sigma p. That's what we want to find effectively in this region. So here there will be a density sigma p right at this interface, which is in fact what we want to find out. Okay, so there will be a sigma p in general. There can be a sigma p at this interface. There is a rho p1 and rho p2 in the two volumes, and on the interface there is a sigma p, which is really what we want to investigate, what we want to find out right at this dA around this point capital Q, in the neighborhood of which we want to find again sigma p, local form. We need to use the integral form of whatever was Gauss's theorem in the previous video for the polarization vector P. So what does it tell us? Okay, so what that theorem tells us is that the overall charge, so the overall charge QP in this coin, so the charge QP, the entire polarization charge in this coin, which is a little volume, is given by three terms. So we need to integrate over the coin, which is in region, the part of the coin in region 1, okay, which is this region up here. And there we will have rho p1 times dV, whatever is the volume element of that part, half of the coin, basically. Then we have the surface, the charge on the surface, which has an area dA, of what we intend to find, which is sigma p times dA. And finally, we have plus the volume integral on the volume of the coin in the space below, in capital omega 2. There we have rho p2 dV. Okay, so this is the total charge in the coin. This is just by definitions of all these charge densities. Now, what about the physics of the problems, which comes in here? The physics is what I call it a sort of Gauss's theorem for capital P. Well, it's minus the surface integral on the entire closed surface of capital sigma coin, which is the lateral surface of the coin. Okay, so this coin is characterized by a surface, an entire surface capital sigma coin, which is comprised of three parts, the two bases and the lateral surface. Okay, and here we need to compute in general P dot n dA. So we cannot resort to the divergence of P. We need to use the integral form, which is this form here. The integral form is always valid. the local form, the differential forms, not always, because lots of vector calculus assumptions go into that, so you cannot always use it. This is always valid with the minus sign, because it's the charge entering, as we know. The minus sign is quite important, obviously. All right, so now that we have all that in hand, what is the next step? Well, the next step is that the coin is characterized by a certain height. So let's say that the height of the coin, which let's say is this quantity here, so this quantity, let's call it h, the height of the coin. As we've done in all cases 2 in piece 242, we want to go in the limit for h, that the height of the coin, we want to go to 0 plus. And why is that? Because we want to squeeze the coin until it becomes just an area in the neighborhood of capital Q. So under these assumptions, what do we find? Well, the first thing we find is that dV, which is the volume, for example, of any of these two volume elements, any dV will be given by, of course, if you really want to be precise, dV, let's do it properly. Let's say dV in region 1, and then the same thing for region 2, is going to be the height divided by 2, okay? It's half of this height times the area, the base, which is dA, okay? And in fact, this is exactly the same as dV2 in the second region. So in this limit, this becomes what? We have a differential, an infinitesimal dA, and h goes to 0, so it's another infinitesimal, it's a higher order infinitesimal, so effectively we can say that all these quantities, they go to 0 plus as well, mathematically. All right, so that's quite useful. In addition, under this condition here, the other thing that happens is that n1 effectively becomes n, they end up coinciding with each other, whereas n2 becomes minus n, picking up another minus sign, exactly as we have seen in 242, in piece 242. Now, with all this in mind, what about this equation here? Well, clearly, if it happens that these volumes are infinitesimal of higher orders, does it really do the contribution from these volume integrals on coin 1 and coin 2, which are really dV1 and dV2 if you want? So if you really want, let's be precise, let's write dV1 and dV2 to keep it consistent with what we wrote there. Well, clearly these are infinitesimal of higher order, so we can neglect the contribution from these two integrals. So the only contribution left is from this integral here, which is on a dA of a dA surface. Clearly, what that gives under this limit is nothing but sigma pdA. The integral over dA of sigma pdA is nothing but sigma pdA because I'm integrating over an infinitesimal area. Okay? On the other side, what do we have? Well, there is no contribution from the lateral surface. The lateral surface gets squeezed down to nothing under these conditions, so the only contributions that you can get are from the bases, which also have an area dA, okay? So you're going to have, let's do this step, so it's minus the surface integral on dA, which is, let's say, the base in region 1 of P dotted with n1 in that region, okay? What P do we need to use? P1, because that's the P vector at this point here. This is my P1 vector. And similarly, there will be a generic P2 vector down here. So we have P1.n1 dA. The lateral surface doesn't contribute, so the other flux we need to consider is plus the flux over dA of P2 dot n2 dA. All right. Now, we are integrating some flux over dA on dA. So clearly, like here, we can rephrase this as sigma pdA on the left-hand side equal to, obviously this one is P1.n1 times dA, because it's an integral over dA in dA. But what is n1? n1 is n. So it's P1 dot n with a minus sign in front of it. Here, n2 is minus n, so I get a minus from this, but another minus here, so I get plus. So minus is plus, and of course, I need not to forget the dA, which we will erase at the end. So the integral is still there. So this is dA. And here, minus is plus, P2 polarization vector in region 2 dotted with n, again minus minus is plus, dA. Now all these dAs clearly cancel out, 1, 2, and 3, and so we are left with the final expression we wanted to find. Let's do it in blue as before, and this tells us that sigma p, the polarization charge at the interface between 1 and 2, these two dielectric materials, is going to be P2 minus P1 vectors, is P2 minus P1 dotted with n, okay? So this is the expression we wanted to find for an interface between two different, each homogeneous dielectric material. I remind you that in 242, for example, typically, when we had Gauss's theorem, it was something like this. It was E1 local case 2. Local case 2 is E1 minus E2 dotted with n, and these n's, they both go, let's be precise here, from 2 to 1, so we are using exactly the same notation. Also this one goes from 2 to 1. This was basically Gauss's theorem, right? It's local form case 2, so it has to be sigma, whatever sigma we have, at the interface divided by, in that case, epsilon naught. All right, so note that here we go P2 minus P1 dot n to 1, and here E1 minus E2 dot n to 1. So there is this discrepancy. Why is that? Because of this minus sign, which comes from the fact that this charge is appearing within the object, which means charge conservation principle. So that's why there is this minus, this difference in the minus sign. It's not a mistake, it's perfectly fine. People do lots of mistakes because they tend to write 1 minus 2 dot n to 1. That's wrong. It has to be like this if you keep using the same notation and going from 2 to 1, which is what we do in all these courses. All right, so now, what happens as a special case? Suppose that as a special case, we say that, for example, the volume, the region 1, let's say, is vacuum. So let's hypothesize that omega 1, what happens when omega 1 is actually vacuum? Well, so then, effectively, I'm considering the interface here between a single homogeneous dielectric material and vacuum, okay? So there is vacuum in omega 1, okay? So under these conditions, well, it so happens that, obviously, in vacuum, can I polarize vacuum? I cannot polarize vacuum. P1 is 0. Therefore, sigma p, in that specific case, when I'm looking at the interface of a single, effectively homogeneous material, which is a subcase of this more generic case, that's why I've done it like this, is going to be P2 dot n to 1, which typically people drop, since there is only one P, they drop the indices and they just say that it's P dot n. P dot n. Okay, so now, if you remember, in the equivalent charge distribution for distribution of dipoles, what did we find there? Well, we found that sigma equivalent was given by the funny P, which is a general case of this P for molecules. This is for molecules, this is for anything, for any distribution of dipoles, whatever it is, and dotted with n. So we find exactly the same expression. This is a subcase of that. We just kept this funny P, we call it this P. But of course, they are the same, okay? So, but now we found it from this physics approach instead of a purely mathematical derivation, we found it from physics, okay? Which is much more beautiful in my opinion. And so from physics, from the same expression, P dot n, it's obviously n vector, is sigma P, okay? When one of two is vacuum. So now in Piazza, I ask you to calculate the case when, for example, omega 2 is vacuum. What happens in that case? I know that typically, in all this course, we will always assume that n, if I have an object, the n unit vector points outside towards vacuum, okay? So we always choose it in such a way that n points towards the vacuum, okay? And that's a convention. So I want you to think about that case when this role is inverted. So to summarize this video, finally, we were able to go back to the concept of surface polarization charge. So we started intuitively from that, okay? We have done this little block of material in a uniform external field, and we saw that there is a polarization charge at the surfaces. But in that case, there was no volume charge, so we had to do a longer discussion to understand the volume charge, which allowed us to find this general equation, which is general for everything. And so if I have an interface between two materials, each of which is homogeneous, but they are interfacing each other, and they're different, so then I cannot use the divergence, as we have done in the previous video. We need to use the integral, which is case 2. And so with the minus sign, not to forget. So when we do this in the limit, this coin squeezed down to in the neighborhood of point capital Q, which is at the interface, we end up finding that sigma p is the difference, is nothing but the discontinuity of the normal components of P, because that's what this means. I'm projecting P2 and P1 over N. So this is the discontinuity of the normal components, which is similar to case 2 for the electric field in 242. The only difference is that this is 2 minus 1, this is 1 minus 2, because of this minus sign here, charge conservation principle. If 1 of 2 is vacuum, we end up finding this expression of sigma p, which in fact, if you go back to the volume which we investigated a couple of videos ago, where we had, for example, charges, we had negative charges. I believe if the field goes this way, that's the way we had it. So we have negative charges here at this interface and positive charge on the other side. If you want to find the sigma p associated with these negative charges here, so let's call it minus sigma p if you want, well, you need to use an equation like this. So you need to know what is p, and you need to define an n. For example, n could be this n here. If that's a simple surface like this is my n. And then somebody needs to give me p, which if the field E was uniform, we will see this later on in the course. If this was my E naught, well, p will be directed also along E naught, as we know, because we are polarizing uniformly in that direction of the molecules. And so by means of this p dot n, I can actually compute sigma p. We will do examples on that. And so with this, we conclude this first general discussion about the surface and volume polarization charges. We have done it in many different ways. So we have done it mathematically. We know that dielectric materials are a distribution of dipoles. We know that distribution of dipoles can be represented by means of equivalent charges, sigma equivalent and rho equivalent. That's mathematical. Then we look at the intuition behind sigma p in the case of dielectrics, which is this intuition here. But then we wanted to understand why there is a volume charge in the case of non-uniform fields. And then we found this kind of Gauss theorem for P, which in the case of non-discontinuous materials, homogeneous materials, allows us to find the divergence of minor divergence of P equal rho P. And then eventually we went to a discontinuity in which we need to use this with a coin type surface, which gives us sigma P at the discontinuity. And when one of them is vacuum, it gives us sigma P right at the interface with vacuum of any dielectric material. That's it.